In this video, we're going to cover some interesting calculus results that you get when you're dealing with inverse functions, and we're going to explain them using a useful Desmos animation that you can pick up and use for your own homework problems. So be sure to stick around and pick that up afterwards. So let's dive in. So before we dive into the calculus of inverse functions, let's start with pre-calculus. Let's start off with what is an inverse function? Basically, an inverse function is a function that undoes another function. And something that I like to think about is opposite steps in opposite order. So here you can see that in these tables, we have examples of inverse functions. So if we're starting out, we have, x squared and square root of x. Now, how does this work? Basically, the idea is that as we plug in a certain input, so in the first case, if we plug in 2, you can see that if we plug that into the first function, so plug in 2 for x to the function x squared, obviously we get out 4. And then you can ask yourself right after that, what would happen if we then take that 4 and plug that into the function f of x? Well, what's the square root of 4? 2. So you'll notice that we get out exactly what we put in. The functions undid one another. So whatever we did to get from 2 to 4, that gets undone to go back from 4, to go from 4 back to 2. And you can see this happens with the other ones as well. 3 squared gets us to 9, but then the square root of 9 is 3. So we're back to what we started with. And that's a common theme with all of these. No matter what we plug in, if these really are inverse functions, then we should get out what we started with. If you apply one function after the other and basically take the output from the first one and feed it into the input from the second one. You can see a similar thing over here. So here we're doing two things actually, if you think about it. Multiply by 2, then add 3. So again, think of the mantra opposite steps in opposite order. So -3, then divide by 2. So each step is undoing the other step and they're happening in the opposite order. As you try that out, you can see that as we plug in 2 here, we will get out 7. But then if we take that 7 and plug it into the inverse, we get back the original, just like we did before. And that's true with these other ones as well. So this is how inverse functions behave. And again, every function may or may not have an inverse. A lot of them do, most of them do, but that's what effectively we mean by inverse functions. So one thing that's useful to be able to do with inverse functions is to be able to tell if two functions are inverse without actually checking every possible input and making sure that if you choose a certain input and then run it through both functions, you get the same thing out. Because that's not even possible anyway. It's not even possible to plug in every single possible input because there's an infinite number of inputs. So how could we do that? Basically, we want to kind of abstract what we've already done. So think about what we did here. The key idea is that we plug in some value. We plug in 2, 3, 4, but let's plug in an arbitrary value x. And then let's plug that into this first function. And again, we don't know what the actual number is, so the best we can do is kind of represent it abstractly. So it's like g of x. But now here's the key. We're going to take that g of x, and then we're going to plug that into the next function. Whatever this number is as an output, we'll take the whole thing and plug it into what we think is the inverse function. And then how would we represent that? Well, in this case, the best way that we could represent it is with f of g of x. We're taking the entire input g of x, the output from the previous stage, and we're just stuffing it as the input into the second stage. And here's the key. If these are the same, if the number that we start out with over here is the number that we end up with over here, then these two functions really are inverse functions. And you can see in this case they really are, because if you plug in x, well, you'll get, what will you get? You'll get x squared for g of x. But then if you plug that into the square root of x, the square root of x, if you plug that function in, you will get basically the square root of x squared, which really is x. So these are the same. In other words, as long as that happens, you really are dealing with an inverse function. So another way to think about this is that this constraint is, in some sense, a way of defining what inverse functions are. You can think of this as the pre-calculus definition of inverse functions. Basically, if you have two functions, f and g, and the order doesn't really matter, you could do g as a function of f and it would still be true. But basically, if you can take any x, and this is important, if you can take any x, not just one x, but every possible x, and plug it into both of them, if you plug it into both of them like this, plug it into one, then take that output and plug it into the other, if you always get what you originally started with, the functions really are inverses. If there are any where you don't, the functions are not inverses. So that's the way you can tell. Okay, so let's run with this idea. And this relationship, this function gets a lot clearer, in my opinion, when you visualize specific points on the function. So what I'm going to do is I'm actually going to plug in x equals b, and then we're going to see what happens. So if you plug in x equals b to this function, you can see that you get f of g of b equals b. And then you can basically do some definitional tricks to make things easier to understand. You can basically say that g of b equals a, and if you make that assumption, then you would also have f of a equals b. So that's kind of what we get out when we look at things this way. What does this actually mean? It means that if this is, for example, the function f, this red function, basically, if you plug in a specific a is kind of your input, if you want to think of it like that, on the original function f, and then you get out a certain value b, so in this case, like a is 1, b is 2 for the inputs, what that means is that on the inverse function, there should be a point b comma a. So in this case, it would be if 1 comma 2 is on the original function, then 2 comma 1, so right here, this should be on the inverse function. So this would be like b a. So that's what that means effectively. If you plug in a to the original and you get b out on the original, then on the inverse, you should be able to plug in the output and get out the old input. So that's kind of the idea. In other words, every point a comma b on the original function gets transported, if you want to think of it like that, to another point b comma a on the inverse function. So the inputs and the outputs are swapped at every point. What this means is that if the inputs and outputs are swapped everywhere at every point, what that effectively does is it acts like a reflection across the line y equals x. And again, I won't go into the details of why it does that, but hopefully just by looking at it, that's kind of believable. So if I go like up here, for example, hopefully it's believable that if you do a reflection transformation, and by the way, a reflection from geometry, what it means is if you have a point and you want to reflect it across a certain line, basically you find the shortest distance to that line, which is always by definition going to be perpendicular. And then the reflection transformation says just whatever that distance is, go the same distance on the other side. And wherever you land, that's the point. And you can do this for every single point. So like right here, if you reflect it across the line, would end up here. So we can already get a pretty decent idea of what the inverse function is going to look like just by doing that. The inverse function would have to look something like this. And this is really just a consequence, remember, of swapping all the inputs and outputs at every point. Swap all inputs A and outputs B get swapped so that B is the input and A is the output for the corresponding point on the inverse. And this effectively looks like reflecting across the line y equals x, which is this dotted line in the middle. And here you can see on this Desmos animation the same behavior as we graph these two inverse functions. The way I like to think about this is that if the xy plane was a sheet of paper and we folded the paper along the line y equals x, imagine what would happen to every single point. So specifically on this point right here, if you imagine this is a sheet of paper with us folding along this dotted line, this would be folded along there. And this point would land over here as you just fold this giant piece of paper. So that's how you can kind of in your mind visualize a reflection transformation, is if you can basically fold it across and one would land on the other. At least that's how I like to think about it. Cool. So that's basically what we mean when we say inverse functions. Now, everything that we've said so far has had nothing to do with calculus. Everything we've talked about so far has just been pre-calculus. So the question is, what does calculus have to say about inverse functions? So at this point in calculus, all we really know how to do is one thing, and that's take the derivative. So let's just take the definition of inverse functions from pre-calculus that we have right here, and let's take the derivative of both sides and see what happens. So let's give that a shot. So if I start out with this, so that's the definition, I'm just gonna take the derivative of both sides with respect to x. And actually, I'm gonna be a little lazy with how I write it. I'll just do it like this. So imagine this is the derivative with respect to x of both sides. So now, what would this be? And again, you kind of think of this is sort of doing implicit differentiation if you want to think of it that way. But basically, what is the derivative of x? Well, just 1. Hopefully that makes sense. And then this, this is for an arbitrary f and g. We don't really know. Basically, we're going to need the chain rule. So the derivative of the outer function, f prime, evaluated to the inner function, g of x, and then times the derivative of the inner function, according to the chain rule. That's what it would be. So we get this function, and then hopefully it makes sense that if we rearrange this, I'm going to basically isolate g prime of x. You can see that we get this 1 over f prime of x, or sorry, f prime of g of x. And we just divide this on both sides. So there we go. This equation is what pops out of calculus. If we just take the definition of inverse functions from pre-calculus and take the derivative of both sides, rearrange a little bit algebraically, we get this result. Now, what does this mean? That's what we have to dive into. Now, this equation that pops out makes even more sense if we think about a specific point. So let's plug in x equals b like we did before in the pre-calculus case and see what happens. So as we go through that, let's see. So we get g prime of b is going to equal 1 over f prime of g of b. But if you remember from before, we said that based on our definitions, the way we were thinking about it for the points, we decided to say that f of a was b, just for simplicity, and that g of b, therefore, was a. So we can actually simplify this. This is g of b right here is a. That's the input on f that happens to be the output on g. So if we plug that in, you can see what happens. We get g prime of b equals 1 over f prime of a. And again, this is really the same equation as above. It's just easier to think about when we plug in specific points like AB and BA on the inverse. So there we go. This is what pops out. Now, what does this actually mean? What this means is that the derivative of g of x at a certain point, our inverse function, is equal to the reciprocal of the derivative of f of x, the original function, at the corresponding point. Now, and note that this is the positive reciprocal, not the negative reciprocal, like you see when you're dealing with, like, for example, perpendicular slopes. This has nothing to do with perpendicular slopes. This is the positive reciprocal. So let's take a look at what this looks like visually to understand what's really going on. So remember, the derivative of f at a certain point is the positive reciprocal of the corresponding point on the inverse. And that derivative at any point is the slope of the tangent line. So here you can see that whatever the slope of f is, the slope on the inverse, g, is 1 divided by that. So here, for example, if I make this for simplicity, if I move that to 1, you can see that the slope on the original here, this orange one, is 2. So what that means is basically at this tangent line, at this point of tangency, the slope of the tangent line is up 2 over 1, slope of 2. Well, on the inverse, it's 1 over that, the positive reciprocal. So up 1 over 2. So you can see that. So basically, that's the idea. And this is true everywhere as long as these functions really are inverses. So you can see as I drag these corresponding inverse points, this is always true, the positive reciprocal. And ironically, you can see that they're actually parallel or the same slope when the slope is 1 about. And you can see I'm pretty close right there. If I go to 0.5, you can see I'm perfectly at 1. So that's kind of a special case. But for these other cases, you can see the slope here. So that's the basic idea. Now, one other thing I want to point out is that, remember, let's go back to that analogy that we talked about before, where we imagine the entire plane, the entire xy plane, as a sheet of paper that gets folded over this line, y equals x. When you think about it like that, doesn't it make sense that these slopes would have to be the positive reciprocals of one another? Because that's the only way visually that this tangent line here would land on that one, is if the slopes are the positive reciprocals of one another. You can maybe visualize that more to kind of convince yourself, but that does have to be true. So that's one way of thinking about it, and that's a deeper way of understanding why it has to be true. So there you go. This single equation is what calculus has to say about inverse functions. It's useful in certain situations where maybe you want to find the derivative of one function at a certain point, if you only know the inverse. You can also use this to derive the derivatives of certain functions if you know the derivatives of their inverses. This is how you find, for example, this is one way, or probably the best way, to derive the trig derivatives, for example. All of these use cases we'll talk about in later videos, but that's basically the theory behind what the theory behind derivatives of inverse functions. So I hope that all makes sense. Feel free to check out the Desmos animation we used for this video in the description, and I will see you next time.